Okay, in this video, we're going to talk about double replacement reaction. So here's a slide summarizing what double replacement reaction would look like. Okay, first of all, I want to briefly explain what the word of precipitation means. Precipitation means when you have two solutions, okay, or any phase of solution, chemicals, okay, and they both are homogeneous, clear solution, and when you mix them up, and the solid coming out from look like nowhere. Okay, so those solid are called precipitate, and this process usually is called precipitation. It basically means it makes solid from liquid. Okay, usually, okay. Now, this is one kind of precipitation reaction. Of course, there are like many chemical reactions that will produce solid from liquid, but we're talking about double replacement here. Okay. So when you look at the chemical equation, these two, okay, if we take a closer look, you will see these are all ionic compounds. Okay, you should recognize sodium as a metal, sulfate as anion, cation anion, cation anion, cation anion. Okay, now the only thing is the sodium sulfate, okay, and the silver nitrate. You can pause here to practice how to name these compounds. Okay. Turn out into be silver sulfate and sodium nitrate. So it look like, okay, they have exchanged their partners. So the cation of the first compound bound with nitrate, which is the anion of the second compound, and the other pair of cation and anion will bond together form another compound. So that's basically what double replacement means. There are two couples exchanging their cation and anion partners, counter ions. And so is this one, this reaction. You can see iron 3 iodide. Okay, iron is a type 2 metal, and the strontium hydroxide. And then later on, you will find iron hydroxide and strontium iodide. Okay, one of the things you should have noticed that is the little numbers here seems to be different. Okay, that's because between the products, over here, between the products and the reactants, okay, you have to be careful what these little numbers are due to their change. They're not changing their charge. Okay, that's the thing. Like silver is a type 1 metal with positive 1 charge. We already talked about that in module 5. Okay, and sodium is positive 1 charge as well. So the charges are not going to be different between reactants and products as ions. Okay, sulfate is negative 2. Let me change a different color. Negative 2, nitrate, NO3 is negative 1, sulfate here is negative 2, nitrate is negative 1. So you can see between sodium and sulfate it's positive 1, negative 2, so you need 2 sodiums to balance the charge, so 2 to 1. Silver and nitrate is 1 to 1, so there's no number. Okay, the 3 belongs to nitrate. Okay, so this is a 1, actually, 1 to 1. Now over here, if you bond silver with sulfate, then things are going to be a little bit different. Okay, you see there are two silvers because silver has positive 1 charge, sulfate is negative 2, so you need two silver here. Whereas between sodium nitrate is 1 to 1, so it's going to be 1 to 1. Again, 3 is part of the nitrate. Okay, so that's the thing you need to be careful. Okay. You can quickly look at the second equation, see if you understand the ratio or the little number changing. Okay, you can pause here. Now, when you come back, you should notice that this iodide is negative 1 each, but this 3 shows there are 3 iodides, so total is negative 3. So this iron, since there's no number, that means this iron is 1 of iron with positive 3 charge. And so is the other iron on the other side. Strontium here is group 2, okay, type 1 metal, positive 2 charge. Hydroxide is negative 1, that's why there are 2 hydroxides. Okay, this 2 is showing there are 2 hydroxides. Now over here, since iron is positive 3, so that's why hydroxide needs the number 3 down here. It's negative 1 each. And strontium is positive 2, and iodide is negative 1, so there's still 2 down here. Okay, now because the numbers are different of the 3 iodides over the 2 iodides, we need to balance the equation by doing that. And then we're going to get into detail about this. Okay, so basically here's the summarizing what happened between 2 ionic compounds. Again, it has to be 2 couple of cation anion pair, and they're going to exchange their partners. Okay, forming AD and CB. The reason we write Cp is because we always put the cation in the front, the positive charge in the front. All right, let's look at a few more examples in details, okay? So typically for a double replacement reaction, there are a number of questions you'll be asked, either in the test or in the homework, okay? First of all, you will be given, let me make it smaller, okay? First of all, you'll be given a half reaction, basically giving you reactants, okay, like this one here. And then you will have to identify the ions, identify the cation anion of each compound. And then you're gonna recombine these two, four things, okay, two couple of cation anion, predicting products over the other side, okay. Crisscross method will show you what that look like, okay. And then once you form the products over here, then you need to balance the equation. And you're gonna write a full ionic net ion equation. We're gonna talk about that in a minute, okay? So let me make it smaller so I'll have enough space to work on things, okay? All right, so let's look at the first equation, chemical here, group of chemicals here. They're fairly straightforward because they're all simple ions, no polyatomic ions here. K2O is called potassium oxide, okay? So potassium oxide, excuse me. Potassium oxide plus AQ, of course, is because it's in water. And the magnesium bromide in AQ as well. Now, we have to list out all of the ions presented in two compounds, like cation, anion. No, cation of the potassium oxide is K plus with the positive 1 charge. Okay. Now, don't bring this 2 down here because that's not part. This 2 is not part of the potassium. It's just showing 2 of the potassiums, okay? Oxide is O negative 2 charge. You have to know the charge of this kind of elements, okay? Magnesium is plus 2 charge. And the bromide, again, bromide is negative 1 charge without 2 down here, okay? You only keep those little numbers when you see a polyatomic ions, okay? Well, actually, that could be in progress as well. But anyway, so no 2 down here. Now, crisscross method is you're going to cross the first cation to the anion of the second compound, and same with the other 2. Okay, so you can form new combination. So between K and Br, not only are you going to write them together, okay, you have to examine that what ratio, what charge they have. The charges are going to be the same over the other side, but what ratio do you need to balance the charge? So positive 1, negative 1, so they're going to be fine just 1 to 1. The other thing is you're going to put down Mg and O. Of course, Mg in the front, O second. So you're going to have plus 2, negative 2. So they can be fine as 1 to 1, 2. So you don't need 2 potassium or 2 bromine here, okay? So these 2 are going to be your new products, okay? Now, next thing is use solubility rule to predict what they are. Just want to remind you, okay, we've said that this is actually about making a solid, aqueous solution. Now, one of these 2 products, at least one of them, okay, has to be a solid to precipitate out. That's why it's called a precipitation reaction. So how do I know which one is going to be precipitated out? You actually go into my courses, and then if you go to, excuse me, course 302 section, and then under course contents, if you click into (1025) survival guide, and currently we're on module 6. Okay. And you can download this, okay? You can pull down this manual and then download this. If you download this, or you don't have to, okay? If you scroll all the way to, I think this is page 7. Okay, this is page 7 of the module 6 on the survival guide. Okay, so here's a table. You can see this is a table that shows you, let me see if I can zoom this up. This is a table that shows you the solubility information between the number of combination of number of cation and anion. So you can see the column here, you have all of the cations with a positive charge. And on the bottom row, you have all of the anions with a negative charge. Okay, and then if you cross-link what we are looking for example, if you look at the magnesium, which is right here, and oxide is right here. So if we move up here, magnesium oxide is I. This is I, okay? So if you found to be I stands for insoluble or partially soluble, which means it's going to remain in solid form. So that means MgO, magnesium oxide, is actually going to be a solid. Okay, keep in mind what you see here is actually I. Okay, now if we look at potassium, okay, the other product is potassium bromide. Okay, if you look at the potassium and then cross to, potassium bromide, which is bromide is down here. Potassium bromide, which is AQ. AQ stands for aqueous, which means this compound is soluble. Okay, so you're going to use this chart to determine the solubility of most of the compounds you should be able to. We're going to discuss in this class. Okay, you don't have to memorize this table. This table will be provided to you in the test. Okay, look for the fact sheet along with next to the exam on my courses. Okay. All right, so basically now we've identified the solubility of these two products. Okay, and the next thing is balanced equation. All right, so let's erase this to make more spaces. Okay. Now, when balancing the equation, we're really trying to balance in. If we draw a broad line separating the reactant side from the product side. Okay, so the reactant side, you have potassium, oxygen, magnesium, and bromine. Technically, you need to balance every single element of all on the reactant side and with the product side, okay? But for double replacement, just for double replacement, okay, you basically just need to list out all 4 ions. But because we're looking at two ionic compounds, right? So we're looking at 4 ions, 2 cations, 2 anions. So we're going to list out all of them in order, in no special order. Okay, let's say I usually do it from left to right. On the reactant side, you have potassium with a positive 1 charge, oxygen with negative 2 charge, magnesium with a +2 charge, and then bromine with negative 1 charge. Now, don't worry about those numbers yet. Okay. Now you're gonna do one by one instead of list out all of the numbers right away. So we're gonna do potassium first. Over the reactant side, you have, because there's number 2, okay, you have 2 potassium. Now over the other side, the only thing that contains potassium bromide is KBr. Now you can't change what this KBr is, okay, because the ratio is 1 to 1. That's determined by the charge of potassium and the bromine. You can't change the formula. The only thing you can do is by putting a big coefficient in front of the molecule. So in this case, you do need to have a number 2 as the coefficient times 1. Okay, so you originally have 1 potassium, so now you're gonna put a 2 here. Now, of course, by putting a 2 here, you are doubling everything, the entire molecule, but that's okay. Okay, we'll deal with that later. Now, potassium is balanced, and then you go to oxygen. Remember, don't write out all numbers. Deal with one element at a time, okay? So the oxygen currently is 1 over here, and over the other side is 1. Okay, that's balanced. Magnesium is 1, and over the other side is 1. Now, here's the thing. Once you balance any 3 out of 4 items, because you're guaranteed having only 4 items, right? Cation, anion, cation, anion. Now, once you balance 3 out of 4 items, the last one should be automatically balanced. You should be able to check this, just like that. Now, of course, you still want to double check if it is. If it's not, then you probably did something wrong. But so this could be a check mark or milestone of the work. Okay, so bromine here, because the little number 2 down here, that means there are 2 bromides or 2 bromines. Now, quite constantly. When you try to balance potassium, you put 2 here, and this 2 also applies to bromine, so that makes 2 bromine as well. So that works out perfectly well. Okay, and that's the thing. If everything you did correctly, then everything should work out perfectly well. So the only coefficient you need is 2 kBr. Everything else will remain as 1, 1, and 1. Okay, so that's balanced equation. So basically, let's look back a little bit. Okay, there are 2 processes you have balanced. First of all, you have to balance the charge internally among each compound. Among the ions and cations, and then you can balance the entire equation by putting coefficients. The first time when you balance charge, you're going to put different little numbers at the bottom. Okay, the second time, you're going to balance it by putting coefficient in the front. Okay, so we've done that, we've done all of these. Okay, now write a full ion equation. What does that mean? Same thing when we make more space here by erasing all of these. Let me rewrite this. Okay. Now the full ion equation is going to be basically expand all of these molecule compounds into separately, break them into cation, anion form. So we're going to write all of the ions out. Okay. Notice that we never put any charge on top of these guys when you are writing them as compound. These are compounds. But once you break the compounds into cation, anion, like what we did before, then you have to highlight the charge on top by putting little numbers. All right, and you have to include a number of things. Okay, how many coefficients? So let's do this. I usually do it from left to right. So K2O. So the potassium is the cation with a positive 1 charge, and there are 2 of them. You can't put 2 down here anymore. Okay, you have to put this 2 in the front, because this is not a polyatomic ion. Okay, when you put writing the potassium ion only, it has to be a big number in the front. And of course, it's the entire compound is aqueous, so this potassium cation is also aqueous. So plus oxygen as the anion. Everybody has to be in the ionic form. Okay, oxygen with -2 charge. And there's only 1 oxygen, okay, so you don't need any number here, so aqueous. So you can see here, we're writing this compounds as separate form like this. This is basically from potassium iodide. But you don't have to write a parenthesis here, okay? I'm just trying to show you where is this from. All right, so if we keep going to next compound is magnesium bromide. So magnesium it has positive 2 charge. The charge is very important, aqueous, since this aqueous here, plus bromide with -1 charge, aqueous. But don't forget that there's a little 2 down here, so you need to put a 2 up here. Well, ideally you would write this in 1 line, but I'm running out of space, so I'm gonna switch the line down here. The products, KBr, potassium plus 1 charge, aqueous, and then there's a big 2 in the front, so of course that 2 goes with the potassium. Okay, plus bromide, Br, -1, aqueous. Also, this 2, like we said before, this 2 applies to potassium as well as the bromide. So there's a 2 in front of bromide as well. Now, the only thing that's exceptional is if you have any solid, okay, the solid does not break up. Just remember that. The solid is hard. It can't break up solid. So you only keep the molecular form of this precipitate. Okay, this is the net ion equation. Basically, you're writing everything out in ions form, cation, anion, cation, anion, cation, anion, except the solid product you form at the end. All right, so that's check. Net ion equation. After full net equation, net one is going to be simple. Now, when you look at the net ion equation, okay, you will find some ions or some species, they are not changed at all before and after reaction. They are so-called spectator ions, such as potassium. There are 2 potassium aqueous. There are also 2 potassium aqueous. So that means this guy is just hanging around, not doing anything at all. Before and after reaction, it's still the same. The other one will be 2 bromide. Okay, now whatever left over is going to be our net ion equation, which will be oxygen -2 charge, aqueous, only one of it, plus magnesium aqueous +2 charge, which is this one. Alright, single arrow, and over the other side there's only one solid left. So this is the net ion equation. So you can see the net ion equation shows the essence of this chemical reaction. The magnesium and oxide forms a product that's turned out to be solid, no longer dissolved in water anymore. Okay, so this is the first example of double replacement.